So the first law of thermodynamics states that in an isolated system, such as the universe, energy can neither be created nor destroyed. It can only transform from one state to another, or transfer into or out of the system, but the total energy never changes. The total mechanical energy of a system remains constant. It's a very important concept here, especially when we're talking about the work energy theorem. So therefore, conservation is attributable to energy transfer, and work is exactly that, is the transfer of energy, is the change in energy in a system. And we define this principle of work and energy using what's known as the work energy theorem here. Oops. So work is performed by externally applied forces and torques other than gravity, and causes a change in energy of that specific object. As I mentioned earlier, there are different types of mechanical energy. There's kinetic, potential. There's also thermal forms of energy, but we're going to ignore that for this module. And we're mainly going to concentrate on kinetic energy and potential energy. And more specifically, we'll just make it simple. We're literally just going to concentrate on work in the linear sense or translational sense. So therefore, we're interested in linear kinetic energy and potential energy. So let's take a look at a simple example here. Say we got a diver just standing up there on the platform. So while he's standing on the platform, he has maximum potential energy, because why? He has the potential, his energy has the potential to shift over the kinetic energy. He's not moving, so therefore kinetic energy is 0. His potential energy is directly proportional to his weight and the height in which he's standing. Then he jumps off the board as he is essentially coming down. He's a projectile, so therefore his displacement in the vertical direction is directly related to 9.81 meters per second squared, as we described in the previous module. So therefore his kinetic energy increases as he goes down closer to the water, while his potential energy decreases. In fact, according to the work energy theorem, the amount of kinetic energy increase should equal the amount of potential energy decrease, and that can go back and forth. And so if we look at a pendulum, for example, in the vacuum of space, because a pendulum will shift back and forth in terms of potential and kinetic energy, according to the law of conservation of energy, the first law of thermodynamics, technically that pendulum will go on forever and ever, because there's no friction, there's no viscosity in the vacuum of space. So here, I'm going to show you this video. This is from Professor Lewin out of MIT. It's probably one of the more popular videos that were made. Gosh, this must have been over maybe 15 years ago. And so he nicely describes the concept of the conservation of energy and the exchange between potential energy when the ball is at its highest point, and kinetic energy, and which will be maximized when it reaches its lowest point, and then back to potential energy. So check this out.
I am such a strong believer of the conservation of mechanical energy that I am willing to put my life on the line. If I release that bob from a certain height, then that bob can never come back to a point where the height is any larger. If I release it from this height and it swings, then when it reaches here, it could not be higher. There is a conversion from gravitational potential energy to kinetic energy back to gravitational potential energy, and it will come to a stop here. And when it swings back, it should not be able to reach any higher, provided that I do not give this object an initial speed when I stand here. I trust the conservation of mechanical energy for 100%. I may not trust myself. I'm going to release this object, and I hope I will be able to do it at 0 speed, so that when it comes back, it may touch my chin, but it may not crush my chin. I want you to be extremely quiet because this is no joke. If I don't succeed in giving it zero speed, then this will be my last lecture. I will close my eyes. I don't want to see this. So please be very quiet. I almost didn't sleep all night. 3, 2, 1, 0. Physics works, and I'm still alive. See you Wednesday.
That's pretty funny. Did you hear that student at the end scream a little bit? I think I screamed a little the first time I watched this. But it's a perfect example. He made a point that as long as he lets go of that ball with zero speed, that means zero initial velocity, just lets it go, then the potential, the gravitational potential energy will convert to kinetic energy as it's moving, and it'll reach its peak at the bottom, and then it'll convert back to potential energy on the way back up, and should reach the same height. In fact, over time, because of friction, it'll eventually slow down, and the height of that ball will also eventually decrease. So its maximum height should be the height in which Professor Lewin, in this case, let go of the ball. So that's simple pendulum. In fact, next week or in the next module, when I start talking about gait, walking gait is highly efficient because of this concept of a pendulum. In fact, it's often described as an inverted pendulum, of this nice conversion of potential and kinetic energy. So anyway, that's a little bit of a preview for next module. Okay, so let's take a look at the jump. We discussed this a little bit before. We talked about acceleration and how particularly during takeoff, how a person who's performing a counter movement jump has positive acceleration going down and going back up, and they'll be able to take off. Now I'm going to take a look at the landing, and we're going to use the work energy theorem to describe the work it takes to bring a jumper's center of mass to a complete stop during landing, and be able to use that concept or that relationship to quantify the displacement in which he or she does that. So I'm going to go ahead and play this. In this case, we're looking at the takeoff. Person's in the air, that's projectiles. Now the person's lands with a certain impact ground reaction force at a certain velocity. So from there, we can calculate the work required to bring his or her center of mass to a complete stop, as well as the associated vertical displacement. Okay, this is a cool video. This is actually a preview for module 9 when we're talking about jumping. So let's take a look at the landing part. I'm going to put up some numbers here, and this is actually in this week's Korsky IRAD. So I'll give you an example of how we could calculate this. So the person's landing from jumping. What we're interested in here is the energy absorbed, aka the work performed to bring the person landing from a jump. So we know that there's gonna his or her center of mass is going to displace in the vertical direction, and we can use the work energy theorem to calculate what that is. So what I have here is exactly that. This left side of the equation, if you look at it, net force multiplied by height, that is work. Right? That's the work performed to displace the center of mass with a certain net force. That is equal to the change in kinetic energy. That's what this is. Right? That is the work energy theorem. So let's take a look at landing. I have here Jim landing from a drop vertical jump, and we can calculate the work required to bring his center of mass to a complete stop using the work energy theorem. Remember, this is 1/2 mass times velocity squared. That's kinetic energy. The change in kinetic energy is simply the final kinetic energy minus the initial kinetic energy. And the best way to explain or describe this is to use an example. So this is Jim. Jim and Jane. I don't know why I'm using Jim, but Jim has mass of 70 kilos. lands with a vertical ground reaction force of 1800 newtons and a vertical velocity of negative 6 meters per second. How much work is required to bring his body to complete stop? For this specific question, we don't even need this part. All we need is velocity. So what is the scenario says? Jim landed with a vertical velocity of negative 6 meters per second. So how much work is required to bring his body to complete stop is dependent on that change in kinetic energy. Well, what does he want to do? He wants to come to a complete stop. So therefore, the final kinetic energy is obviously 0. The initial kinetic energy, it's governed by this equation, 1/2 his mass times velocity squared. So if you do the math, enter 70 kilos for his mass. He landed with a velocity, vertical velocity of 6 meters per second. You square that, you end up getting negative 1,260 joules. Why do you think it's negative? Well, think about it. He landed with a certain vertical velocity. He wants to come to a complete stop. Is he absorbing or generating energy? Well, think about his acceleration. Is he decelerating? Is he slowing down while he's moving into negative direction? Yes. So therefore, he has negative acceleration. The change in energy in this case, because he's going from some velocity, in this case 6 meters per second, to 0, so therefore energy is being absorbed at a magnitude of negative 1,260 joules. Therefore, there is negative work performed. The energy is being absorbed by his muscles. Again, if you ever get confused, go back to anatomy, go back to phys. What do you believe the muscles are doing during landing in this case? And you can pick any muscle. I often choose the knee extensors as an example because it's easy to visualize. We know that this person's landing, they're flexing their knees, but it's controlled knee flexion. And it's controlled by what? The quadriceps. What are the quadriceps doing in this example when during landing from a jump? Are they eccentrically firing or concentrically firing? If you said eccentrically firing, you're exactly correct. They are contracting while lengthening, so therefore they are absorbing energy. That's why you have negative work being performed. Now, by extension, we can use the work energy theorem to calculate the displacement of the center of mass. And this is the exact same equation I showed you. This is work. This is the net force multiplied by displacement, and you set that equal to the change in kinetic energy that we found here. So negative 1,260 joules. Do the math, and then you solve for z. So go ahead and try that on your own. And if you go ahead and pause this video, and then I'll tell you the answer here, which is negative 1.13 meters. That's what you should have got if you did the math correctly. Okay, good. All right, so finally we'll talk briefly about efficiency of movement and economy. I mentioned this in the beginning of the semester, that if I had to describe biomechanics, and more specifically the application of biomechanics in sports or in human movement in general, can best be described by efficiency and economy of movement. You think about injury risk and performance. The more efficient an athlete moves, the lower their risk of a certain modifiable. The lower the modifiable risk of certain injuries. Right? Take an ACL injury. If they're efficient at landing from a jump or doing a cut, they can minimize the risk of an ACL injury. Performance. If they can maximize performance with the least amount of energy, they are a lot more efficient. So at the end of the day, as a trainer, as a physical therapist, whether we're working on prehab and trying to minimize the risk of injuries, or we're working in rehab and trying to get an athlete back to pre-injury levels, what we're really doing as a clinician is improving their efficiency of movement. Right? And we do this with a number of different training interventions and modalities, etc., etc. But how we do that ultimately determines how efficient an athlete or a patient ultimately becomes. So let's take a look at the definition of efficiency. Essentially what this means is the amount of mechanical energy that can be expended with a given amount of input. And really I should put it here metabolic energy if I wanted to here. So it's how much output I can get out of a given amount of metabolic energy. Perfect example is your car. When you, or more specifically gas, we measure gas in terms of fuel efficiency. How many miles can you get per gallon, right? And so same thing with this. If we have a certain amount of metabolic energy, a certain amount of VO2 max, how much output can I get out of that when I'm performing something? How much fastball speed I can get from someone performing certain movements, or a pitcher moving their pelvis and their trunk and the shoulder in order to create a 95, 96 mile per hour. Can I improve someone's ball speed by doing certain techniques, using weighted balls or using balance or core stabilization exercises, for example? That's how you improve someone's efficiency, by improving their output. And you can measure both in the absolute sense as well as percentage. So if you improve someone's output, then you improve someone's efficiency. Okay. Now, economy is something similar to that, except in this case you want to know how much input is needed in order to create a fixed output. So for example, look at runners. Runners, as you know, run fixed distance. They run a mile, they run a 5K, they run 26.2 miles. And so a runner becomes more economical when they use less energy to achieve that distance. And we measure that typically with what? With time. You know, if someone, a track and field athlete or a cross country athlete is able to finish a mile in under 5 minutes, under 6 minutes, somewhere around there, that runner is more economical than someone who finishes it in 7 minutes or 8 minutes, because they use less energy in order to finish that distance. So depending on your perspective, depending on if you're interested in using less energy to achieve a certain output or getting more of output for a given amount of energy, will determine whether you're interested in economy or efficiency. Here I think I have an example here. This is actually from Nike. They use a motion capture system in order to measure the economy of runners using different types of shoes. In fact, we have one grad student in our MS Kin program who is comparing carbon plated shoes such as the Vaporflies that Nike makes, or the Adidas Adios, or the Hoka shoes. Supposedly those shoes improve someone's running economy. We've seen some anecdotal evidence of that, at least in the marathon side of thing. Look at Eliud Kipchoge back in October, who broke the 2-hour barrier in running a marathon and was wearing the Vaporflies. And there is some evidence to suggest that the carbon plated midsoles improves someone's energy input, if you will, when running a mile or running a marathon. So anyway, there are a lot of research to be done in this area, but one of the things that we can use as an outcome variable, as a dependent variable, is what's known as a economy. And that's energy.